thank you for the invitation. I hope you are all having an amazing time in Bratislava and also productive time in Bratislava. Now, as you might have guessed from the introduction and from my title, I believe my talk is not going to add to the productivity part of what you guys are doing, but I believe it's something interesting, and perhaps, you know, I have seen the timetable of this meeting, and I would say that busy is an understatement. So, you know, take this opportunity to sit back, relax, and listen to something little different, hopefully interesting. And to make the job easier for you, I am going to start with what I would like you to remember from what I'm going to say. So if you have capacity for one slide, I would just suggest to remember this one. So when you try to put quantum mechanics and general relativity together, you necessarily end up with space-time that has some discrete structure on small distances. And when I say small, I mean distances of order Planck length. Now, don't worry, this is not going to be a quantum gravity talk, because a certain way to do this also, independently on that, leads to reformulation of the standard model of particle physics from something I would call for first principles. Now, I'm not here to oversell this idea to you, so you know I'm going to be as honest as possible. But if I was, you know, bidding little, I would remove the quotation marks and claim to have derived the standard model from first principles. And as is usually the case with such stories, we are going to learn some new things and gain some new insights into the particle physics part of my talk. So here are some references. I don't expect you to go and download everything right now. This is basically just to cover my back, because nothing that I'm going to tell you is my own work, obviously. So this is the original reference that this whole business of non-commutative version of standard model started with. Here are some nice reviews, and I don't know if you know that, but Alan Kohn is a Fields Medal recipient, and always when you see Fields Medal recipients doing some physics, we real physicists are up for a bumpy ride. So buckle up. I don't think I need to introduce this to this audience, do I? So this is the particle content of standard model. You guys know much more about this than I do. The only thing that I want you to pay attention to is this red color in contrast with the orange color of the Higgs boson. Yes, that the gauge bosons enter the standard model in a very different way than the scalar Higgs that's there just to break the electroweak symmetry. And you know, if you want it to be a little more theoretical, you would say that the standard model is the most general gauge theory with such a gauge group that describes the observed particle content. On the general relativity side, this is the usual thing that you put in, that Google returns when you Google for images of general relativity. As we are all aware of, this is very nice, very good looking, but horribly wrong depiction of how general relativity works. This is a little better depiction of how general relativity works. And we are already starting to see some tension in between the two in this equation, because when you know, standard model is a quantum theory, so the matter enters here in T mu nu as operators on some Hilbert space, whereas the space-time enters through these quantities, which are geometric quantities, and they're not operators. That's the bottom line. So this equation now makes absolutely no sense, yes, because we're mixing oranges with apples. And the question of quantum gravity is how do we reconcile this tension? And I like to phrase this tension as a discrepancy between algebraic theory of quantum mechanics and standard model, i.e. something expressed in terms of operators on Hilbert spaces, and geometric quantities derived from the metric tensor of the space-time. And we're going to return to this idea of reconciling the tension between the geometry and algebra soon. Okay, I will mention something about quantum gravity because the motivation is a little bit in there. So I don't know if I need to somehow persuade you that this thing is correct. What is when you try to naively insert hats on the blue quantities and try to without too much thinking repeat the formalism of quantum field theory for objects of general relativity, you obviously can do that, and obviously you run into trouble because you get a non-realizable theory. Yeah. So people have been trying to fix that. You have probably heard about a lot of more or less unsuccessful ways how to do that, but most of the ways you probably have heard of, like string theory, basically tries to make the left part of the equation I have shown you red. They try to reconcile the tension by making the geometric object algebraic, and with varying degree of success. Now, whatever the quantum theory of gravity is going to turn out to be, we have good reasons to believe that at the end of the day, in that theory, our space-time is going to be described very differently than what we're used to. That is not going to be a smooth manifold, but it's going to be some new object with some discrete structure with characteristic length at the order of Planck scale. Now, there's this cartoonish idea of Heisenberg microscope that when you are trying to measure very small distances, you create very energetic particles that become black holes and hide whatever you were trying to see under their horizons. There's ideas stemming from string theory formulations that the space-time itself is an emergent quantity, and that the principal degrees of freedom of the fundamental theory are different. And there's actually an idea that has a reference that says that under quantum fluctuations, the vacuum is unstable, meaning that large, very energetic, very localized fluctuations of quantum theory are going to lead to black holes, and the whole vacuum is very soon going to collapse into a collection of black holes. This is obviously not happening, so something needs to give. And what a way around this, a very simple way around this, is simply to not allow very small quantum fluctuations. That you introduce some kind of fundamental length scale, and you say that under this length scale, the distinction between the 2 points makes no sense, and then you basically made the problematic fluctuations disappear. And when you think about this, this is similar to how uncertainty principle solves the stability of the hydrogen atom and basically of all the atoms. Yeah, as we all know, in classical physics, the proton-electron system is unstable because the electron radiates the energy and falls into the nucleus. But since that would be a state with precise momentum and precise position, the quantum mechanics doesn't allow that, and there's some ground state where the electron orbits at some finite distance. And so you can take this idea and introduce such uncertainty in between coordinate observables, and then you get the what we were asking from in the previous slide, that there is some fundamental volume in the space-time, and we cannot have fluctuations smaller than that fundamental unit, and therefore the vacuum is saved. And the upshot is that this approach preserves at least some continuous symmetries of the space, opposing to something like lattice discretization, which is interesting. You end up with a space that is discrete, but still continuously symmetric. Okay, and this leads to the idea of non-commutative geometry. So the standard geometry can be, at the level of topology, rephrased in terms of C-star algebras. That's maybe, some of you remember this from your functional analysis courses or something similar, that instead of thinking about the manifold itself, you can think about the algebra of functions on the manifolds with pointwise multiplication and pointwise addition. And then, if you think really hard, you can rephrase everything regarding the topology of that space using this algebra of functions. Now, the idea of the non-commutative geometry is to think what happens when you take non-commutative algebra. Yes, clearly for regular manifold, the algebra of function is commutative because it doesn't really matter in which order you multiply the two functions. But when you are, you can try to ask questions: what happens when this algebra becomes non-commutative? So the program is you reformulate everything you can about the usual spaces in terms of algebras of their functions, and then you let this algebra be non-commutative. Obviously, then the original space is something very strange, because the multiplication of functions doesn't commute anymore, and you pronounce the object that your non-commutative algebra is algebra of functions on as your non-commutative space, and the geometry that this non-commutative algebra leads to as non-commutative geometry. Now, what you need then is an algebra, a Hilbert space, and these two, the Hilbert space where this algebra is represented, and these two things together give you just the topology of the space. You need some new additional information, new data, and the data is a self-adjoint operator, which is an element of that algebra. You pick one particular element of that algebra that defines your geometry, that defines not only which points are close to each other, but defines exactly the distance between the points on that space. Yeah, and the cartoon version, what is that the Dirac operator is the square root of Laplacian up to some nuances, and then the geometry of the space is somehow encoded in the eigenvalues of this operator. Now this is something. Okay, and one thing, because of this is you can see in literature things like spectral geometry floating around. Yeah, the word spectrum appears a lot. For example, the algebra A, the Hilbert space H, and the operator D together are referred to as spectral triple. And the word spectrum comes from the fact that what you're really interested in is the spectrum of this operator D. The eigenvalues of these operators are the key ingredient for your geometry. Now, this is something that you might be familiar with. You probably have heard this question, whether by listening to the eigenfrequencies of vibrations of a shape of a drum, you can tell what drum you're listening to. And if you have a square drum and a circular drum, then the eigenvalues are different, and you can tell, if you take your cell phone and you do frequency analysis on the sound that comes from the drum, you can tell whether the drum was a circle or a square. Now, the question is whether you can tell this all the time, and the answer is no. And for example, these two shapes have the same eigenfrequencies of vibrations. So there's a counterexample to this question. However, as far as I understand, the problem of regions with smooth boundary hasn't been solved yet. That the rough edges of this boundary probably make the difference in here. But yeah, this is just to illustrate that the fact that the eigenvalues of Laplace operator have something to do with geometry, at least of two-dimensional surfaces, thanks to our familiarity with things like drums makes sense. Okay, so finally to something that you are more familiar with, and the claim is that the standard model of particle physics can be reformulated as an example of quite simple non-commutative geometry. Now, what I mean by simple is that the non-commutative part is rather simple, and we'll get later to the fact that it's actually the simplest you can have. So the algebra in the spectral triple of the standard model is given by commutative algebra of smooth functions on your manifold, where you're defining your physics on your space-time, and some non-commutative part, which is 3 times 3 matrices combined with quaternions and combined with complex numbers. Now, if you realize quaternions as 2 times 2 matrices, you can at least a little see how the gauge group of the standard model is going to emerge. Yeah, and there's some technical way how to derive the gauge group from this particular algebra. Yeah, but the SU2 SU3 SU2 U1, it's conceivable that it's there. Now, so this is the algebra. Now we need the matter content. So you take your fermions of the standard model and you create the Hilbert space from these fermions. Okay, so you have quarks, you have leptons. Now you need 2 chiralities, and you need particles and antiparticles, and you need 3 generations of fermions, which altogether gives 96 degrees of freedom. So your elements of your Hilbert space is going to be 96 dimensional Hilbert space, which, from point of view of vector spaces, 96 is not too much different than from 2 or 3. If you have a PhD student who actually needs to do the calculations, then that is very different. But from the conceptual point of view, that's some finite dimensional Hilbert space, and the dimension of the Hilbert space is given by what kind of particles you need to have in your theory. And here comes the first thing, that if you have capacity to remember something beyond the first slide, this is the first thing that is perhaps good to remember. That the way we formulate when we formulate the standard model in this fashion, the matter content becomes a part of your space-time. Yeah? You have shifted the particles and grouped them together with your space-time degrees of freedom. Perhaps this comes to mind. And this goes the other way around in what I said before, when you try to reconcile the differences between the two sides. Yeah, we haven't quantized anything yet. Everything is classical at the moment. But what we are trying to do is we are reformulating the matter content of our space in a similar fashion as the space-time itself was formulated. So we're going the other way around as people who do string theory or similar ideas are going. Yeah, we are not trying to force the left side to be similar to the right side, but the other way around. So now you need to pick your Dirac operator. Yeah, the Dirac operator is a particular element of the algebra A. You take this part, which is, the space-time part is commutative, and it's the usual thing that happens. Yeah, for us, the interesting part happens here in the finite part of the Dirac operator, and yeah, I just wanted to show you how it looks. You can see that I didn't even typeset this. I just copied it from some review that was referenced in the beginning. Yeah, the dots are 0, and these are matrices of usually 3 × 3 size, where the important thing is that the elements of the matrices basically contain the Yukawa couplings that end up in the Lagrangian, in your Lagrangian. So you're basically free to pick up any 96 × 96 matrix, but if you want at the end of the day to obtain the Lagrangian of the standard model, then this is the way to do it. But for our discussion, we picked a particular 96 × 96 matrix that is going to lead to reasonable standard model Lagrangian. So the fermions are part of your Hilbert space, and you want to construct your action. So your action is going to be just the scalar product of action of your Dirac operator on your vector with the vector itself. And this scalar product also includes the space-time integration over the commutative degrees of freedom. And you can imagine how this thing here leads to the mass terms for fermions. Yeah, if you multiply, you have psi here, you have psi here, so you pick up various mass terms for the fermions, which are elements of the 96-dimensional column vector psi. Obvious question is, where are the bosons? Where do we and how do we get the gauge fields? And the gauge fields are given as fluctuations of the Dirac operator. Yeah, so you allow your original matrix to fluctuate. This A is determined by how your algebra looks, and this part of your algebra gives you gluons. Yeah, the fluctuations in A that are part of this algebra are going to be gluon fields. okay, this should have been sorry, the quaternions and the complex numbers. One give you the fields that eventually become the W and Z boson, and C gives you the field that, after the B field that then in the standard spontaneous symmetry breaking leads to, apart from other things, to the photon. But this is the next point that's worth remembering, that the gauge fields are now fluctuations of the internal space, of the finite part of your algebra, and the Higgs boson becomes the part that fluctuates within, just within the finite part. So we have reconciled the difference between the red bosons and the orange boson, that now all these are understood as one thing, and that's as fluctuations due to the finite non-commutative part of your algebra in your spectral triple that was used to define the standard model. Their bosons are understood on the same footing. Yeah, they are essentially the same object, or object of the same quality. And moreover, the gauge fields are now fluctuations of the internal geometry, of the non-commutative part of your geometry, in a similar fashion as your gravitational degrees of freedom were fluctuations of your space-time geometry. So this is the second point that, if you have capacity to, I would be really happy if you could remember, that in this formulation of the standard model, all the bosons become something similar to the fluctuations of the space-time geometry. Yeah, and all the bosons are now, we understand all the interactions in terms of fluctuations of some kind of geometry. The price we had to pay was the non-commutativity of that geometry. Now we need action for our bosons. This is called a spectral action, where you take trace of some function of this form, where lambda is your energy cutoff and chi is some kind of cutoff function, which is usually taken as a characteristic function of 0, an interval from 0 to 1. So in that case, this just counts the number of eigenvalues of d smaller than lambda. And there are some different technical ways how you can do this, but essentially this is the idea, that your bosonic action is the number of eigenvalues of your Dirac operator smaller than some cutoff. And you write down the theory, you write down the bosonic action, you write down the fermionic action, and you in literature they usually say that you crank the machine, which again usually means that you let your PhD student compute traces of 96 by 96 matrices. Hopefully you have bought Mathematica for them or something like that. And there's a lot of work to be done. The interesting thing that happens there is that the Yukawa couplings, the coefficients of the Dirac operator that I have shown you, they depend on the Yukawa couplings of the fermions, but nowhere enters parameters of the Higgs potential, the vacuum expectation value and the quartic coupling. Moreover, those two things are actually functions of the Yukawa coupling. So you can calculate the Higgs mass. It includes some kind of renormalization ideas and one loop calculations. This is your result. Now, depends on how you look at this number. It's either great or not so great. I'm going to put it in boldface because this is the third, and I promise the last thing that I suggest you remember beyond the first slide. Why is it great? Because when you hear theoretical or mathematical physicists do predictions, you maybe remember the prediction of the cosmological constant being 120 orders of magnitude larger than it truly is. So if you have a mathematical physicist predicting this for a mass of Higgs, then it's quite okay, isn't it? However, no matter how you try to put it, 170 simply is not 125, and as I have described it, this formulation is wrong. But it's not too wrong. Obviously, there is something interesting going on because we didn't get a number that's 120 orders magnitude larger than the observed value. So usually people say that this suggests that this is an interesting starting point with a lot of upshots. And if you phrase this correctly, this is also an upshot. So it's something definitely worth working on. And why is it worth working on? Because there's a natural way how to go beyond your standard model. Yeah, you just consider something different for your finite part of the algebra and see what happens. And the interesting thing is that you have much fewer possibilities than when you consider gauge theories and group theory. Because we are working with algebras, and you need an associative finite dimensional algebra. So you're basically left with real numbers, complex numbers, and quaternions, and matrices of these. That's one thing. And the second thing is representations of these are much simpler than representations of groups. And technically, there's only trivial representation and the defining representation. And the mathematical reason is that when you're representing groups, you need to respect only one property, or one. You only need to respect the group multiplication. When you're representing the algebra, you need to keep track not only of the multiplication, but also of the summation in the algebra. So there are the representations of algebras are much more constrained, and therefore you have much less leeway, and there's much fewer things that you can try. And if you impose some technical conditions on the fact that you want to have particles and antiparticles, and that you need your Hilbert space to split into left-handed and right-handed particles, then this is what you end up with as the most general thing you can have for some integer n. So you try your integers. Integer n equal to 1 doesn't lead to anything. N equal to 2 leads to Paty-Sala model, where SU2 is enlarged to SU4, and hypercharge U1 is enlarged to SU2. And you can try to see what happens there. Obviously, at least at low energies, you cannot have Paty-Sala. You need to have the standard model, so you need to somehow break this larger symmetry into the standard model symmetry. That includes one extra scalar particle, which means you have more particles. However, using this particle, you can fix the Higgs mass to be consistent with the observation. So people who sell the non-commutative version of Paty-Sala model sell it saying that it predicts the Higgs mass consistent with observations. The price you have to pay is a new field that hasn't been observed yet. N equal to 3 case doesn't work. And n equal to 4 case is something that people are working a lot on because it has some promises, but there are some issues with that. But yeah, when you try to formulate beyond standard model physics in this language, you are much more constrained than when you're doing the standard, let's say the standard gauge theory things. Well, with that, let me, for those of you who have forgotten the first slide, let me repeat it. If you try to formulate consistent quantum theory of gravity, it looks like you cannot go around changing the structure of your space-time. There is a way to introduce this structure that borrows some ideas from quantum mechanics called non-commutative geometry. And as a surprise gift, this formulation using the non-commutative geometry can be used to reformulate the standard model with some insights, and if you try really hard, you can sell it as derivation from first principles. And the 3 insights that I mentioned today were the fact that the fermions become part of your underlying manifold, the bosons become fluctuations of this manifold in a similar way that the gravitational field is fluctuation of the geometry of the space-time itself, and you can get predictions for things like Higgs mass. And with that, I thank you for your attention.